Howdy Pima students. This is Module 1B. So this is where it was a little tricky. In Module in Module 1B, we're still in Chapter 2, which is the chemistry chapter. But this is Part A2 of the chemistry chapter. So there's a video before this that introduces you to chemistry. And if you watch the other video, then you know this table is the periodic table of elements. And some, like we went over last time, some really important elements in the periodic table of elements, at least important in terms of anatomy and physiology, are carbon, hydrogen, oxygen, and nitrogen, or if you remember from the last video, CHON. And some people even put phosphorus in there, so, well, phosphorus and sulfur, so CHON's P. So chemical reactions. This is kind of interesting. Table salt, right here in this cartoon. Here's some table salt. Its chemical name is sodium chloride. But those two elements, you don't want to eat. So the first element, sodium, is a metal. So it's a silvery metal, and you can actually cut it with a knife. I mean, the knife has to be kind of sharp, but you can cut sodium with a knife. And then chlorine is a poisonous gas. But you put them together in their ionic forms. So what I mean by that is sodium as a positive ion or a cation, and chlorine as a negative ion, aka an anion. You put their ions together and you get delicious table salt. So, and this is a chemical reaction, and that occurs when atoms or molecules, in this case, this instance, we have two atoms or molecules combine with, or they dissociate, that means break apart, from other atoms. So in this chemical reaction, sodium ion plus a chloride ion, and then you see the arrow goes this way, makes sodium chloride. And if you remember the items on the left side of the arrow are called the reactants or substrate. I think in these, the term substrate more in physiology and the term reactant more in chemistry. And then on the right side of the arrow, sodium chloride, that would be the product. So when you combine atoms together, you're using chemical bonds. And we'll talk about what all the different types of chemical bonds that we're interested in anatomy and physiology. When atoms break apart from other atoms, that happens when the chemical bonds break. And then when atoms combine, that's when the chemical bonds are formed. So some terms, molecular formula. That the molecular formula identifies the number and types of atoms in the reaction. So for example, in our formula, a molecular formula, or we also called it a chemical reaction, can be both. The molecular formula that we looked at, one, and you don't see a 1 in front of the sodium, but it's known, if there's no number in front of your atom, that means a 1 is there. So you have one sodium ion combines with one chloride ion to form one molecule of sodium chloride. Another example, you have 4 hydrogen atoms plus how many carbons? If you said 1, you were right. 4 hydrogen atoms plus 1 carbon atom combine together to make one methane molecule, CH4. It's a molecular formula. All right, we did this in the last video, but this is a quick review. Subatomic particles, we have protons, and neutrons that each one weighs 1 atomic mass unit, and then the electrons, and they virtually have no mass. And electrons can be found in these things called shells or orbitals. We won't get into the details, the chemical details of this. We'll just call it a shell or an orbital. And the first shell or orbital can hold up to 2 electrons. So hydrogen only has 1 electron to put in its shell, so it only needs its first shell. Helium has 2 electrons it needs to put in 2 shells, and just so happens the first shell can hold 2 electrons. Helium's good with 1 shell. Now lithium, check this out. There's 3 electrons that lithium has to put in 2 shells. You can only put 2 in the first shell, and you can put, for our purposes, we're going to say you can put up to 8 electrons in the second shell. It's more complicated than that, but we're going to keep it simple. So, puts its first 2 electrons in the first shell, and then it puts its lone 3rd electron in the second shell. But that second shell could theoretically hold, or hypothetically hold, 7 more electrons, because the second shell can hold 8 electrons. We've talked about this. Electrons have a negative charge. The mass is virtually 0. Electrons are found in shells. And then we just said this. The first shell can hold 2. Second shell holds 8. The next shell holds 8. And so on. This is really important in understanding how elements bond with each other, or how chemical bonds form. The major player in forming chemical bonding are electrons. There they are, electrons. They dictate the reaction. So where your electrons are in their shells, if the shell is full or not, that dictates if one atom will bond to another atom. So reactions occur generally when atoms do not have full outer shells. For example, hydrogen. Hydrogen's outer shell, it's only the first shell, but it only had 1 electron. That shell is not full for hydrogen. So it needs another electron, and hydrogen will be looking for another electron to fill its shell. Lithium, check it out. Its outer shell has 1 electron, it can hold 8. So its outer shell, lithium's outer shell or orbital, is not full. If your outer shell is not full, then you, as an atom, are unstable. And you will react with other atoms to try to gain stability. So if you are an atom, and you don't have a full outer shell, you will react to either gain electrons, lose electrons, or you can share electrons until their outer shell is full. When your outer shell is full, you are stable. And who doesn't want to be stable? I mean, we all want to be stable, right? So do atoms. If, on the other hand, an atom is stable, it does not react with other atoms. Check it out, helium. It's got 2 electrons in its outer shell. Its outer shell happens to be its first shell that can hold 2 electrons. It's stable. Its outer shell is full. It's stable. If you are a stable atom, you are also called unreactive. That means if your outer shell is full and you're stable, you're not looking to react to try to fill your outer shell. You are also called inert. If you're stable, you're inert. You have full outer shell, you don't react. Some chemically inert elements. We've already looked at helium. Here's neon. It's inert. So check it out. You need to know how to play this game. If on a test you are told that you have a neon atom, that means that it's electrically neutral. That means it has 10 protons, 10 positive protons, and 10 negative electrons. 10 positives, 10 negatives cancel each other out. It is an atom of neon. It is not an ion of neon. Now, if you have 10 electrons, you have to put those 10 electrons in their shells. So you can put 2 of the 10 in the first shell, and that first shell is full. Now, you have 8 electrons left to put away. Remember, this second shell can hold 8 electrons. Boom, there you go. You got your 8 electrons in your outer shell. Your outer shell is full. You are inert, aka stable. Way to go, Neon. If, however, you do not have a full outer shell, then you will react with other atoms until you are happy that your outer shell is full. And we've already talked about hydrogen, so hydrogen is reactive because it doesn't have a full outer shell. Carbon, so carbon 6 means it has 6 electrons, so you put 2 in the first shell, 4 in the second shell out here. Remember, the second shell, to be full, needs a total of 8, so it needs 4 more electrons. So carbon is reactive. It will react with other atoms. Oxygen has 8 electrons. It puts 2 in the first shell, 6 electrons in the outer shell. It needs 2 more electrons to be stable. So oxygen is chemically active, aka chemically reactive. And then sodium, check it out. It's got 11 electrons it's got to put away. So it puts away 2 in the first, 8 in the second shell. That's a total of 10 electrons put away. And then it's got its 11th electron out here in the third shell. And the third shell can hold up to 8 electrons, and it's only got 1 in it. So sodium is a reactive atom or element. And now we're going to say that the outermost, this cartoon just shows you that you can also call that outermost shell the valence shell. And they're also calling it an energy level in this cartoon, but we won't really go into the energetics of valence shells. But the outermost shell is also called the valence shell. Okay, this is a new cartoon. It's just a piece of the periodic table of elements. And it just kind of shows you some tricks to reading the periodic table. If you are in this first row, remember rows go left to right, columns are vertical, so they go up and down. If you are in this first row on the periodic table of elements, that means that you have electrons in your first shell only. So you can have either 1 electron in your first shell, or you can have 2 electrons like helium in your first shell. But the way to read the periodic table of elements is this first row. You're only using your first shell to put away electrons. In the second row, so here's lithium, beryllium, etc. The second shell means that you need to use your second shell to put away your electrons. And you can see in this cartoon, lithium is using its second shell, beryllium is using its second shell to put away its electrons, and on down the line. If you're in the third row here on the periodic table of elements, that means you need 3 shells to put away your electrons. And you can see sodium, for example, needs 3 shells, and we talked about that earlier, to put away its 11 electrons. And then to read this, the atomic number is written as a subscript to the left of the symbol. So remember, the atomic number is the number of protons in an atom. The atomic number, it's the number of protons. It can also be the number of electrons in a neutral atom. So that means an atom without. Okay, some more tricks on reading the periodic table. As you go from left to right across a row, the atomic number, that's the number of protons, that number increases. So it shows here hydrogen has an atomic number of 1. Helium has an atomic number of 2. Lithium has an atomic number of 3. As you go across the periodic table from left to right in a row, you go from 3, 4, 5, 6, 7 on up to 10 in neon. Same thing with sodium is 11, you go up to 18 protons in argon, etc. So that's how you can, some tricks to reading the periodic table. The columns, however, that's the vertical column in the periodic table of elements. You have similar electron patterns in your outer valence shell. That means that you have similar chemical reactivity. So, for example, hydrogen, we've been looking at this. It's got one, oh, I'm sorry, I should do this. It's got one proton, so, and this is not an ion, it's a hydrogen atom, so it's electrically neutral, so it also has one electron. Hydrogen has one electron in its outer valence shell. Lithium with an atomic number of 3, so it's also got 3 electrons because lithium is the neutral atom. It's got 3 electrons, puts 2 electrons in its first shell, 1 electron in its valence or outer shell. Same as hydrogen. Hydrogen's got 1 electron in its valence shell. Lithium has 1 electron in its valence shell. Sodium has 1 electron in its valence shell. Potassium has 1 electron in its valence shell. If it's got 1 electron in their valence shells, these elements do, and the valence shell electrons dictate chemical reactivity, then that means every element in this column has a similar chemical reactivity. Okay, so let's check this out. Here's a question. Well, let's look at the cartoon first. If you are a sodium atom, you've got this 1 electron in your outer shell, and here's the chlorine atom, and it's got 1, 2, 3, 4, 5, 6, 7. So it's got 7 electrons in its outer shell. Sodium has 1 electron in its valence shell. Now, think about it. Is it going to be, what's going to be easier for sodium to do? To find 7 more electrons to give it 8 in its valence shell? Or would it be easier for sodium to just lose this or transfer this valence shell electron to another element and then fall back down to its next valence shell, which has a total of 8 electrons in it? Well, obviously that's the easy way, and that's what sodium does. So, and then chlorine, the chlorine atom, if it's in the vicinity, will allow the transfer of that electron from sodium to chlorine. Now check it out. Chlorine becomes an ion now because it's got 8 electrons in its valence shell. So now if sodium has lost 1 negative charge, it's lost 1 negative electron, that means it's going to become more positive because it lost 1 negative charge, and it's going to become more positive by 1. So that means that where you once were the sodium atom, you were electrically neutral, now you have lost 1 negative charge. So you're going to become more positive by 1. And there's no 1 there, but you have to, it's just a plus sign, but you have to know there's a 1 there. And now you're called a sodium ion. The chlorine atom took on an extra negative charge, becomes the chloride ion, and it's got a negative charge of -1. And now the question, the reactive properties or chemical behavior in an atom mostly depend on the number of D, the electrons in the outer shell of the atom is the answer. Okay, now we talked about this, but just remember an ion is an atom with a net charge. And that means the number of protons does not equal the number of electrons. like it does in a neutral atom. An ion is formed when you have a neutral atom, like sodium, for example, gains or loses an electron to become stable. So remember, with sodium lost its outer shell or its valence electron and became a positive sodium ion. Ions, if you have oppositely charged ions next to each other, they will attract. Remember, opposites attract? So that's why sodium, positive sodium, negative chloride ions, they're attracted to each other and they form table salt. So some positive ions, we said sodium has a +1 charge. Now look, if it's not just one, they'll actually write the number there. So calcium has a +2 charge. So that means it must have lost, that the calcium atom must have lost 2 negative electrons and therefore become overall, therefore have gained an overall positive charge of +2. And then if you're a negative ion, you're gaining electrons. And there's our cartoon again. All right, ionic bonds. Guess how they're formed? If you said ionic bonds are formed between 2 ions, you're right. And in anatomy and physiology, we're interested in ionic bonds because you find them mainly in the teeth and bones. So this attraction that they have for each other leads to stability. So sodium and chloride being attracted to each other, the positive sodium ion and the negative chloride ion being attracted to each other and forming an ionic bond makes that sodium chloride stable. So, and electrons in ionic bonds, electrons are completely transferred from one atom to another, and we saw that. Chloride or sodium gives up its outer shell electron to chlorine. Chlorine takes that extra electron. So you get a complete transfer of one electron from sodium to chloride. In chemistry, if you're a salt, so in common parlance, we use salt, we just think it's table salt. But in chemistry, a salt is anything that has an ionic bond. So there's sodium chloride, table salt. There's also potassium chloride and lithium chloride. So there's a whole bunch of different salts in chemistry that we don't have to worry about because, you know, we are not in chemistry in this class. And then this just shows, here's a cartoon. This is what we've been talking about all along. I hope you really use this cartoon and, you know, draw it out yourself and really kind of understand. Play with these electrons, play the electron games. Oh, that sounds fun. I should invent a game, the electron game. How to transfer electrons around and make new molecules. So I like this cartoon here, this letter B, this cartoon. It kind of shows a salt or a cube or a piece of salt in 3 dimensions. So it looks like it's more like a rectangle in a cube, but it shows here's the chloride ion being larger than the sodium ion, but you can see you don't have, the key to looking at this cartoon is you don't have a bunch of negative chloride ions all, say, inhabiting one area, because like charges, so a negative charge and a negative charge, they will repel each other. So you're going to have this nice formation where you'll have the negative charges and the positive charges as close as they can be to each other. Okay, so that was an ionic bond, our first bond in anatomy and physiology to talk about. The second bond we want to talk about is a covalent bond. Covalent bonds are really, really important in anatomy and physiology because they're everywhere. So you have to really big on covalent bonds. And this is a table from Marriott, from your book, Alternative Ways to Represent Four Common Molecules. So the four common molecules would be molecular hydrogen, molecular oxygen, methane, you know, that's gas, and then water, the water molecules. Those are four common molecules that we deal with all the time on this earth. So here's the molecular formula. We just looked at that. And then in this next column, so we're gonna use the term columns and rows because you know what that means now in the periodic table of elements. But in the second column, we have an electron distribution diagram. So H2, that's a molecule. That's two hydrogen atoms, and here they are. Here's the nucleus of one hydrogen atom. Here's the nucleus of another hydrogen atom. And because they are sharing their electrons, that's called a covalent bond. So remember, in an ionic bond, chloride, sodium, they got close to each other. Sodium gave up its electron completely to chlorine, and then chlorine completely took that electron. There was no sharing. And that left sodium as a positive ion and the chloride ion as a negative ion. In these covalent bonds, atoms will share their electrons. They don't completely strip an electron from one atom. And so this is what it looks like in the cartoon. So remember, hydrogen, it needs two electrons to fill its valence shell to be stable. So H2, or molecular hydrogen, is stable because each of these hydrogen atoms are sharing these two electrons. So they each have one, each hydrogen atom has one outer shell electron. When two hydrogen atoms come together, they share their valence electrons, and that's called a single covalent bond. So they're sharing electrons. Covalent means to share electrons. And now the term covalent is going to become more, a little more complicated because you can share your electrons either equally or unequally. But for now, we're just going to say that a covalent bond is where when two atoms share one or more pairs of electrons. So the hydrogen, to form molecular hydrogen, you're sharing one pair of electrons. In molecular oxygen, O2, you share two pairs of electrons. If you share two pairs of electrons, that means you have a double sharing bond or a double covalent bond. So you can see here these two oxygen atoms. Here's an oxygen atom, here's an oxygen atom. They're sharing these two pairs. So remember, in one pair you have two things. If you have a pair of shoes, you have two things in a pair of shoes. They're sharing two pairs of electrons. In methane, the gas, carbon, it's got four outer shell electrons. Each hydrogen atom has one outer shell electron. So check it out. One carbon atom, this guy right here, is sharing one pair of electrons between four hydrogen atoms. So here's one hydrogen atom. Carbon is sharing one pair of electrons here. Carbon is sharing one pair of electrons. Carbon is sharing one pair of electrons with this hydrogen. Carbon is sharing one pair of electrons with this hydrogen. And they're sharing, each carbon-hydrogen covalent bond is sharing one pair of electrons. So these are single bonds. And then water. Oxygen is sharing one pair of electrons with this hydrogen atom and one pair of electrons with this hydrogen atom. And what that does is that makes the hydrogen atoms, their outer shells are full, and now oxygen, its outer shell will be full with 8 electrons. And again, this is, they're sharing one pair of electrons, so that means it's a single covalent bond. Most chemical bonds in the body are covalent bonds. They are more stable than ionic bonds, so they're very stable. Thanks, Mother Nature, for making those stable. And this, we just talked about this. Two atoms will share one or more pairs of valence electrons. So we just looked at that. And we looked at table 2.8. Now this is kind of interesting. The number of covalent bonds that an atom can form is equal to the number of additional electrons needed to fill the valence shell. So, for example, carbon. It needs 4 carbon. It's got 4 electrons in its valence shell. It can hold 8. It needs 4 more electrons to fill its shell. So carbon can form 4 single covalent bonds. Or carbon could form 2 double covalent bonds. Covalent bonds can be single, double, or triple bonds. Okay, so we've already looked at this as the single covalent bond. Here's a double covalent bond. This is just showing what we just talked about. But here's one oxygen atom. It's got 1, 2, 3, 4, 5, 6 electrons in its outer shell. That means it needs 2 more to make 8. Here's another oxygen atom, same dilemma. When they come together, 2 oxygen atoms come together, look at this, they can share 2 pairs of electrons, and now their valence shell will be full. So molecular oxygen, that's the oxygen that you breathe, has a double covalent bond. And then here's the, okay, doesn't go backwards. Anyway, so now we're going to talk about, I told you covalent bonds get a little bit more complicated. If you are a covalent bond, you're sharing your electrons, right? So sometimes when you share things, you can share them more or less equally. So like when I was a little kid, have a bag of M&Ms, and I'm supposed to share them with my sister. You know, I give her 1 M&M out of the whole bag, and I'm telling my mother I did share with her. Of course, that was unequal sharing, but it was sharing nonetheless. I could have also split the bag equally in half and given her exactly half the M&Ms and me the other half. So there's different ways to share. If you share equally, you share your electrons, not your M&Ms, but if you share your electrons equally, then you are a non-polar covalent bond. If you share your electrons unequally, then what results is a polar covalent bond. So carbon is a really good sharer. Carbon is, that's what our life forms on this planet are based on. Carbon is a great sharer. And so when it shares its electrons, it will form 4 single non-polar covalent bonds. So non-polar means equal sharing. It's kind of weird that it's that way, but that's what it's called. Non-polar is equal sharing. Non-polar covalent bonds, electrons are shared equally between the atoms in the molecule. I said that. But we didn't say this yet. Non-polar covalent bonds result in an electrically neutral molecule. So, for example, methane. There's no charge. There's no positive or negative charge on methane. Carbon dioxide. I think I have a cartoon of that. Here's carbon dioxide. So here's carbon in the middle. Carbon's usually black in cartoons, and oxygen's usually red in cartoons. So this is carbon dioxide. This carbon dioxide forms a non-polar covalent bond, and it's electrically neutral. You can see there's no charge on carbon dioxide. What about unequal sharing? Polar covalent bonds. Why do they call them polar covalent bonds? Here's why. Because remember, you know, on the Earth, you have the North Pole and the South Pole. So they took that concept and they said, in an unequal sharing of electrons, you will have a kind of like a pole. You'll have a negative pole, and then it's not, you know, just like the North and South Pole, but then you'll have a negative pole where the oxygen is, and then you'll have this positive pole where the hydrogens are. That's why they call it a polar covalent bond. And they also call this structure a dipole. So D-I-P-O-L-E. You can't see the E here because I'm there. But this polar molecule is called a dipole. Now, why does that happen? Because if you are an atom like hydrogen and you form a bond with oxygen, you are forming a bond with an atom that is very electronegative. That means if you are an electronegative atom, you like to hog the electrons in any covalent bond. You have a strong will to not completely steal an electron like in an ionic bond. You'll share your electrons, but most of the time, if someone wanted to find where the electron is in that water molecule, they'd look towards oxygen. So if you are in a polar covalent bond, you're sharing your electrons, but one atom will have a bigger share of that electron. And the other atom, in this case hydrogen, will have lesser share of that electron time. And we said this, a molecule that has polar covalent bonds in it will have a pole, a positive pole and a negative pole. So this is a typical illustration of a polar covalent bond, which is between oxygen and hydrogen. But you can also have a bond between nitrogen and hydrogen that would also form a polar covalent bond or an unequal sharing of electrons. You could also have a polar covalent bond between oxygen and carbon. Those are polar covalent bonds. Which of those atoms, nitrogen, hydrogen, oxygen, and carbon, are electron hogs? Well, we've already said oxygen is an electron hog. But what about these two, between nitrogen and hydrogen? Which one do you think is an electron hog? Which atom is closer to oxygen on the periodic table of elements? If you said nitrogen, you're right. So those elements, kind of on the right-hand side, if you're looking at the periodic table of elements in front of you, kind of on the right-hand side, those elements like nitrogen and oxygen, those guys in that column, in that area, those guys are all electron hogs. And then we'll talk about this a lot later, but I'll just introduce it now. If you guessed that this was a molecule of DNA, you would be right. And it just shows in this cartoon, here's an N and an H. So this is just to illustrate that between the N and the H in DNA, you have a polar covalent bond. Here's another one. Between the O and the H in DNA, you have a polar covalent bond. So you can find polar covalent bonds within molecules. Now, this is really important, that term within a molecule. So this whole thing is one strand of DNA. You guys know DNA is double-stranded, right? And then this whole thing is the second strand of DNA. So within these A, T, C, and G, or adenine, thymine, guanine, and cytosine, probably heard of those, they make up DNA. Within those molecules, you have polar covalent bonds between nitrogen and hydrogen, and oxygen and hydrogen. This is going to be really important. That's within the molecule. Between two molecules, you have these little dashed lines, and those guys hold the double strand together, and those bonds are something new. Those bonds are the third bond we're going to talk about. Those bonds are hydrogen bonds. So we'll have ionic bonds, covalent bonds, and remember, if you're covalent, you have two subtypes of bonds, polar covalent and nonpolar covalent. And then the third major type of bond we'll talk about is a hydrogen bond. Woohoo! Important for 202. They're also important for 205 and 208. Hydrogen bonds are everywhere. They're really important to understand if you want to get A's in your classes as you go forward. They're real weak bonds, but they're everywhere. Now, here, check this out. This is a water molecule. Within, so make sure you understand I'm saying within that water molecule, that single water molecule, between the oxygen and hydrogens, you have a polar covalent bond within the water molecule. Within this water molecule, same thing. Between the oxygen and the hydrogens, you have a polar covalent bond. Now between, so that was within the molecule, between the molecule, so between one molecule of one water molecule and another water molecule, you have these little things. They're represented by dotted lines. Those are called hydrogen bonds. And in a hydrogen bond, remember, hydrogen bonds are between molecules. In this hydrogen bond, this partially negative oxygen is attracted to this partially negative hydrogen. That's a hydrogen bond. This oxygen could be a nitrogen too, because remember, if you're an electron hog, you like to hog electrons most of the time. That means you're partially negative. And then hydrogen is always partially positive. So you have bonds within a molecule and bonds between molecules. So it says the definition, the free hydrogen ion. You could have a free hydrogen ion here. So what that means is you could just have a free hydrogen ion floating out here in space, and you could have a hydrogen bond between that free hydrogen ion and the electronegative oxygen. But you could have the free hydrogen ion or a hydrogen ion in a polar molecule, which is what this guy is right here. This is a hydrogen ion in a polar molecule. It's attracted to the negative portion, that's the oxygen, of another polar molecule. So usually you have hydrogen bonds between polar molecules. Hydrogen bonds are responsible for cohesion and surface tension of water, and that's what this photograph is showing. So this is a water skipper on water. So because these hydrogen bonds, so here's the water out here. This is all water out here. Though there's hydrogen bonds between the water molecules, those hydrogen bonds create this thing called surface tension of water, and that allows this really lightweight water skipper to walk on water. Now, while this isn't, the water skipper's not that important for A and P, but for us, hydrogen bonds are really important for forming intramolecular bonds, like in protein structure. So when we look at carbohydrates, fats, and proteins, we're going to be looking at a lot of hydrogen bonds. So really work hard to understand the concept of a hydrogen bond. So this is just definition of cohesion. That's a tendency of like molecules to stay together. That's like molecules would be water molecules. They're like each other. They want to stay together. That's called cohesion. When like molecules are cohesive, that creates this phenomenon called surface tension. And then you can get these guys walking on water. Okay, summary: covalent bonds, polar covalent and nonpolar covalent, and hydrogen bonds. So in nonpolar covalent bonds, a good example is methane, where the carbon atom shares its electrons equally with 4 hydrogen atoms. And then water is a great example of showing you a polar covalent bond. So it's polar, so you kind of have a positive and negative pole. The negative part of the molecule is going to be where oxygen is, and the positive part of the molecule is going to be where hydrogen is. And then hydrogen bonds, remember, are bonds that form between molecules, not bonds within molecules.